Welcome to This Explainer. Today, we're going to peel back the curtain on a fascinating, entirely invisible world of energy. It surrounds us, it flows through us, and it literally shapes the entire universe. We're talking about the incredible physics of thermal radiation.
So let me start off by asking you something kind of strange. Take a second and just look at your own hands. Did you know you're glowing right now? Yeah, literally you. Right at this very second, you are actually emitting a brilliant, completely invisible light. Okay, let's dive into this. Based on the physics of thermal radiation, a typical person, with a surface area of about 2 square meters and normal body temperature is continuously radiating around 1,000 watts of energy into their surroundings. Think about that. You're basically a walking space heater. Now, to be fair, you're also absorbing about 900 watts right back from the walls and objects around you, but still, the fact remains you are constantly pulsing out this crazy amount of invisible energy.
Section 1. Defining thermal radiation. So, what exactly is this glowing energy? Well, thermal radiation is essentially electromagnetic radiation emitted by the thermal motion of particles in matter. And the absolutely crucial takeaway here is that this happens in all matter that has a temperature above absolute zero. Your body, the chair you're sitting in, heck, even the ice cubes in your freezer, they're all made of atoms and molecules that are constantly jittering around, and this random kinetic movement causes charged particles inside the atoms, the protons and electrons, to accelerate and oscillate. Whenever electric charges accelerate like that, they generate coupled electric and magnetic fields, which then emits photons. Boom. That's the radiation. Now, you gotta contrast this with other ways heat moves. Unlike conduction, which requires direct physical touch, like heat spreading through a metal pan, or convection, which needs a fluid medium, like warm air rising up a chimney, thermal radiation is a whole different beast. It requires absolutely zero physical medium to propagate. It can travel seamlessly through the dead vacuum of space. It's just pure electromagnetic energy in transit.
Section 2. The colors of heat. Okay, so how does temperature actually change this radiation? Well, temperature directly dictates the frequency and ultimately the color of the radiation an object emits. At room temperature, the radiation is entirely in the infrared spectrum. It's totally invisible to us. But as an object heats up, the dominant frequency of its radiation shifts higher and higher into shorter wavelengths. As temperature rises, it goes from invisible infrared to a faint red glow, up through bright orange, and eventually it hits this intense yellowish white. And what's really interesting here is this specific threshold, 525 degrees Celsius, or 977 degrees Fahrenheit. In physics, we call this the Draper point. This is the exact temperature where basically all solid substances first begin to visibly glow with a mildly dull red color. Now, below this temperature, the glow doesn't just completely vanish. It just becomes way too weak in the visible spectrum for our human eyes to actually perceive it. But check this out, because this is a truly mind-bending fact. Even when an object gets incredibly hot, we're talking about an old-school white-hot 2000 Kelvin incandescent light bulb filament, 99% of its radiated energy still remains in the invisible infrared spectrum. No way, right? The brilliant white light we see is just a tiny, tiny sliver of the actual thermal energy being blasted out. Despite that bright glow, the vast majority of that thermal radiation stays entirely invisible to the human eye.
Section 3. Traveling through the void.
Now let's look at how this invisible energy actually moves across the universe. Because it travels as an electromagnetic wave, thermal radiation doesn't just survive in a vacuum. It actually achieves its absolute maximum heat transfer efficiency in a complete vacuum. Out in the void, there's absolutely no physical matter to absorb or scatter the waves. And this incredible property is the primary method by which the sun transfers its massive, massive heat across millions of miles of empty, dead space just to warm our Earth.
Section 4. Our radiant planet. Let's zoom out to a planetary scale for a second. And this brilliantly illustrates the delicate balance of our atmosphere. Over 99.9% of our dry atmosphere, mostly nitrogen, oxygen, and a little bit of argon, is completely transparent to infrared thermal radiation. The heat just passes right through it like it isn't even there. That leaves just a tiny, tiny fraction of greenhouse gases, less than 0.1%, to actually interact with this thermal energy. So let's quickly walk through the step-by-step narrative of the planetary heat balance. Step 1. The sun radiates energy through the vacuum of space. Step 2. The Earth absorbs this incoming sunlight, which warms up our surface. Step 3, and here's the kicker, just like you and me, the Earth acts as its very own giant blackbody radiator, re-emitting that absorbed heat back out as infrared thermal radiation. And finally, step 4, those trace greenhouse gases in the atmosphere absorb and trap a portion of this outgoing infrared heat, keeping it from just immediately escaping back into the freezing void. So why does all of this matter? Well, without those greenhouse gases trapping Earth's thermal radiation, our average surface temperature would be a literally freezing -18 degrees Celsius. That's 0 degrees Fahrenheit. This exact capture of thermal radiation is the very mechanism that keeps our planet habitable, maintaining a really comfortable global average of roughly 15 degrees Celsius. It's pretty wild to think about, right? Every time you feel the warmth of the sun or the heat from another person, you're experiencing the fundamental thermal physics of the universe. We are all basically walking, talking 1,000-watt radiators, living on a giant radiant rock, constantly exchanging invisible waves of energy with the cosmos. So I'll leave you with this. The next time you step outside and feel the warmth on your skin, ask yourself, what other invisible forces are shaping your world right now?